This is Algebra 1, Semester 1, Unit 2, Solving Linear Equations. Now, that might just look like words to you, but I want to make sure that you remember from Unit 1, linear meant straight line. We also may have talked about in class that linear means x's to the first power. So we normally will just write it as x without the power showing. Equations means we could have equals, means we could have inequality as well. Actually, this first section isn't with inequality, or else it would say inequality. So, okay, let's get to the first problem here. It says equivalent equations. Let me make sure that I've got it on the camera right. Yeah, that's good. Equivalent equations, it's just a question. They're just asking us, hey, are these two equal? Easiest thing to do here to see if they're equivalent is to see if the x value is the same amount, because that's your variable. Okay, that's the only way to know if they would be equivalent is if the x's, if this x and this x, should put it in brown, I don't see my brown marker, are equal. Okay, so the easiest way to find that, I mean, you've got a number of ways. Like I've said in math, there's a lot of different methods, but I would take this -3 that this x is equal to and plug it in right there. So the old commercials, you know, like, what was it, Glad? Plug it in, plug it in. Put -3 in there, so we have 2, remember always with parentheses, times -3 plus 14 equals 8. Order of operations, we multiply first, so 2 times -3 would be -6 plus 14 equals 8. Now we add these together, their signs are different, so we end up subtracting them. 14 minus 6 is 8. 8. Those two are equal, so that means yes, these are equivalent. Okay? Next problem here. On these kinds of problems where you're solving for x, where I'm not giving you a value and asking if they're equivalent, I need you to keep in mind that you have to justify. There's a little judge's hammer coming down, or the scales showing justice. I actually think of these differently, guys. I think of these as though they're on a teeter-totter. I look at this part like it's a teeter-totter, and this is one side, and this is the other side. Okay? Now, I'll tell you a really sad story about me when I was in kindergarten. I couldn't wait to go out and play on the teeter-totter because it was just my favorite thing. I always look forward to it every day. And so finally it took me months and months to work up the ability to get first in line so that I could get outside and be on that teeter-totter. And I was sitting on that end just waiting for my friends to come around the corner. My friends tricked me. And the next thing I knew, this kid named Bobby Boomba came running. I loved Bobby. He had a great sense of humor, but I didn't love him that day because he grew into his name. And oh my gosh, he ended up being a really good football player, a lineman. But in kindergarten, he jumped on the end of that teeter-totter, and you can guess the next thing. So what I'm saying is, do not make a mess like that in a problem by getting it unbalanced. If this is perfectly balanced, don't do anything to this side that causes the other side to flip off. Okay? Now, here we go. We look at the x, we circle the unknown, and we say we got to figure out what's happening there. He's kind of the creepy dude. We don't know what's going on, but he's standing out because he's been spotlighted for us. So our next thing is we go up the PIMDAs. And we say, is anything being added or subtracted to that x? The answer would be yes. We draw a line down where our teeter-totter is, so we make sure what we do on this side, we do on that side. And we get rid of what's being added. That wipes out. We have x by himself. That one was easy to solve. 17 minus 9 would be 8. Okay? Now, if you like solving them where you write it up here on this line, that's fine with me. I just do it straight down my teeter-totter. But the next thing you have to do is justify your step. Since you subtracted on each side, your justification is subtraction, property of equality. And what that subtraction property of equality says, if you subtract the same thing from each side, it will stay equal. Okay, kind of a common sense, I know, but it's nice for us to be able to use it in our justification. Now on this one, same thing, we're going to go up the PIMDAs. So we circle our creepy dude, draw the line down at the center of our teeter-totter, and we say, what is being done to our x? There's nothing being added or subtracted, so we climb up the ladder. Now it's multiplied or divide. What's happening is that it's being divided. To get rid of divide, we do the inverse, which is to multiply. Now, if it helps you, you can put that over 1. So, we have 6 and 6 cancel, and we have x alone, and we get 72. Okay? Now, we can justify that with multiplication. Property of equality. The last thing that I would ask you to do when you're doing these kind of problems is go back and check 8, plug it in there, 8 plus 9 equals 17. That one checks. And 72, check it out, 72 divided by 6, does it equal 12? Yes, it does. So that is the next thing on there. Now we have another kind of problem that we want to look at. This problem takes a few more steps, but we're doing the exact same thing. We draw the line, circle the creepy dude. I'm getting rid of that marker, it's driving me nuts. And we go up our PIMDAs. I always want to see this written near your problem. Okay? Going up our PIMDAs, it's just like a ladder. We look at what can be added, or what is being added or subtracted to the x. We look here, 5 is being added. Do the inverse, we subtract. This will wipe out. We get 2x equals 13 minus 5 is 8. Now we can say we've gone up the ladder. There's no more add or subtract over here by this creepy dude. Keep him spotlighted. Next thing we notice is 2 is being multiplied. If he's being multiplied, that means we need to divide to get rid of him. And we have x equals 4. Now, you do need to justify your steps. Right here, since we subtracted on each side, that would be the subtraction property of equality. This would be division property of equality. And now we need to plug in the 4. 2 times 4 plus 5. 2 times 4 is 8 plus 5 equals 13, so it checks. Okay? The last kind of problem that you'll see in tomorrow's, oh no, I have 2 more. Second to last kind of problem you'll see tomorrow is a little bit harder, multi-step problem. Now don't freak out on me. We've already worked on problems where we get rid of fractions and where we get rid of parentheses. Okay? So we're going to clear the parentheses first. Before we ever draw the line, before we ever do anything, we'll clear it by the distributive property. You do need to justify. Now notice I don't write equality. That's because we didn't do it on each side, keeping it equal. So we have 3x over 2 plus 7x minus 7 equals 6x plus 3. Now our next step is, you wouldn't have to, but most of you don't like having fractions. We talked about that in class. You said, yeah, let's clear them. So to clear the fractions, we multiply by a number that will cause every fraction in the problem to cancel. Since we only have a 2 here, we'll just multiply every term by 2. By 2, by 2, by 2, and by 2. Okay? So now we have that canceling. We get 3x plus 14x minus 14 equals 12x plus 6. That would be a multiplication property of equality, because we did do it on both sides. Now we can combine our like terms. So that would be 17x minus 14 equals 12x plus 6. That would be the associative property. Since we didn't do it across the equality sign, we don't have of equality. Now, the best thing to do next, draw your line and get your creepy dudes all in one spot. You don't want them hopping off and running away. You want to know if they're nice or not. So we subtract 12x, subtract 12x. I always have a tendency to bring it to the left because I don't make as many errors that way, and I suggest you do too because it makes inequalities easier. So that wipes out and we get 5x minus 14 equals 6. Now we're just like before. This was subtraction property of equality. When we subtracted the 12x from each side, we're still keeping our equation balanced on this teeter-totter. What's being subtracted now, we can go up the PIMDAs. What's being added or subtracted to the creepy dude is 14. We do the opposite. This wipes out. We get 5x equals 20. And we're done with add, subtract. Now we're at multiply, divide. It's being multiplied, so we divide by 5. And we find that x equals 4. Circle your answer, because sometimes it's hard for me to see those. Okay? Our last steps here, there was the subtraction property of equality. This here is the addition property of equality. And right here we have the division property of equality. And that's our solution. You do need to take this 4 and plug it back in there. 3 times 4 is 12. 12 divided by 2 would be 6. 7 times 4 is 28. 28 and 6 is 34. 34 minus 7 would be 27. Now we plug the 4 in here. 2 times 4 is 8, plus 1 is 9. 3 times 9 is 27. So it does check. And I'd just like you to put the little check right here because I know you may do it on scratch paper too. Okay, I'd like to be able to see your check. Last problem for this lesson. They're going to give you equations like this and say, are g of x and f of x equal? Well, if f of x equals this, and g of x equals this, all they're asking is 3x plus 2, is it equal to, well, let me get multicolored here, negative x plus 10. Okay? They're just asking, are those two equal? You'll do it just like the problem before. Everything in this unit's about keeping things equal, making sure that one thing is equal to the other. So you're always on this teeter-totter. First thing we do is gather our x's. Plus x, because it was a minus x. We get rid of it that way. -1 plus 1 is 0. And now we'd have 4x plus 2 equals 10. And subtract 2. 4x equals 8. X equals 2. So their question was, when are f of x and g of x equal? It wasn't, are they equal, because they both have the variable. They are equal when x is equal to 2. Let's plug it in and check it. 3 times 2 is 6, plus 2 is 8. -2 plus 10 would be 8. Have a great day. We'll see you in class tomorrow.